So the proof of Euclidean algorithm is quite straightforward, and we start by assumption, and we say that GCD of AB, let's say, is equal to some integer d. And what this really means is that d divides A and d divides B, which in turn implies that d will divide any combination of A and B using the rules of divisibility. And the combination that we have selected is none other than the combination that we get from the division algorithm, which says that if you do for any two integers A and B, you can always get a combination of numbers such unique integers Q and R, for which QB plus R equals to A. And what we have simply done is take this to the left hand side here, and that's why it will become minus negative. So when we are actually saying that D divides A minus QB, we are saying that D divides R. So if D is a common divisor for A and B, then D is surely divides R, and then it's also a common divisor for B and A. And if you want to try and prove it the other way around, like let's say okay, D divides B and R, D divides B, and D also divides R, it implies D also divides a combination of B and Q. And again, the combination that we have selected is none other than the one we get from division algorithm, that is BQ plus R, and which we have already seen is equal to A. So it means that D divides A and D divides R. So a common divisor of B and R will also be equal to the common divisor of A and B. So here's a proof of Euclidean algorithm and how we can use it to find GCD for any number, two numbers and two numbers. So whenever we have an equation of the form AX is congruent to B in mod M, we say that these are a linear congruence of variable X, and we can solve this equation for X. And the purpose of this is to find all the integers X that satisfy this congruence. And the solution always exists. Okay. So we're not gonna go and solve these congruencies, but the proof for this also lies in the Euclidean algorithm. And the Euclidean algorithm can be augmented to, and it's called extended Euclidean algorithm, and it gives you, or it finds you all the values of X for which this congruency will be true. So I will leave this as an exercise for you all to explore about extended Euclidean algorithm and how we can use extended Euclidean algorithm to solve congruencies. Right now, we're gonna see another very interesting fact, that if A and M are relatively prime, we always have an integer that we called inverse of A, and it's called multiplicative inverse of A. Actually, I have missed here. It's called the multiplicative inverse of A in mod M. So usually a multiplicative inverse of A does not exist always. It will only exist if A and M are relatively prime. So we altogether skip this topic, multiplicative inverse of A in mod M, when we were studying about modular arithmetic, and we were seeing the uh, modular addition and modular multiplication, and we saw the properties of modular addition and modular multiplication. We saw that both of these operations are closed, and they are reflex, and they have an identity, and all the property, they have associativity, they have distributivity, and we saw all their properties. But I skipped the topic of multiplicative inverse. We also have, we always have the additive inverse of a, and additive inverse of a was always equal to m minus a, because this will always be equal to 0 in mod m. So the additive inverse always exists. There is no condition for additive inverse to exist. But for multiplicative inverse to exist, you have to fulfill the condition that a and m are always relatively prime. So this is a necessity for a multiplicative inverse to exist. And now we're going to do some examples, and I'm going to ask you to find me a inverse of 3 in mod 7 and inverse of 101 in mod 4620. So if we try to make a multiplicative table for modular multiplication in modulo 6, that is, if we have the set of integers ranging from 0 to 5, and we try to make a multiplicative table for this, we can see that you only get inverse for 1 and you only get an inverse for 5, because for rest of the three numbers are not relatively prime to 6, because the GCD of 2 and 6 is 2 itself, GCD of 3 and 6 is 3 itself, GCD of 4 and 6 is 2. So you can see their columns and their rows that we don't have any ones in them. So we cannot find any multiplicative inverse for these three numbers. But whereas 5 and 6 are relatively prime to each other, and you can see that 5 multiplied by 5 is 25, and when we try take a remainder of it with 6, you get the answer 1. And so, therefore 5 has a multiplicative inverse, which is 5 itself. So here's the multiplication uh, in mod 6. So in mod 6, the multiplicative inverse of 5 is 5 itself, and the multiplicative inverse of 1 is 1 itself, and rest of the numbers that comes in the set Z6 do not have any multiplicative inverse. So let's try and find the multiplicative table and inverse of all the integers that lie in the set Z7.